In this lecture, we will explore the concept of continuity. So first, our formal definition. Suppose that f is defined in a neighborhood of the point A. Neighborhood just means an open interval around A. We say f is continuous at A, provided that two conditions hold. The limit as x approaches A of f of x exists, and the limit as x approaches A of f of x equals f of A. If these two conditions do not hold at x equals A, we say the function is discontinuous. So let's draw a picture to understand what this means. So if this is our value A, then the first condition, which I'll circle in blue, tells us that the limit as x approaches A of f of x exists. So as we approach A from the left and from the right, we have to be honing in on some value. So we've got to be coming towards that from the left and then towards that from the right. The other condition tells us that limiting value, so the value that we're approaching from both left and right as x approaches A, the function's value, has to equal the function value itself. So if you plug this A into the function, this value is f of A. And so if we have these two conditions at A, we say f is continuous at A. There are three ways that a function of one variable can be discontinuous at a point. And we can go through each of them. So the first is there's a hole, and that's kind of natural to see. So if we explore these discontinuities, for a hole, it's really something like the picture that we have up there, except we have a hole. Maybe the function is defined up here. So this would be an example of a discontinuity that's a hole. Another type is a jump discontinuity. So in that case, you may have a function that does something like this, but then it jumps, say, up here. And by the way, we can see how the definition doesn't work. In this case, for the jump discontinuity case, the limit from the left differs from the limit from the right, which means number one is not satisfied because the limit doesn't exist. So the function is not continuous at that point. If we go back to the hole, sure, we have a limit coming from both sides. The limit is the same, but the function value is up here. It doesn't match that limit. So it's 2 that's broken with the hole, 1 that's broken with the jump, and then we also have a vertical asymptote or an infinite discontinuity. So in this case, you might have something like this. And in this case, A wouldn't even be in the domain of F. But we have this discontinuity, and again, we can look at what breaks in the definition. In this case, the limit doesn't exist. Remember, we call the limit infinite in this type of case, but that's a type of non-existent limit. It's a characterization of one kind of non-existent limit. So the limit doesn't exist, and also f of A doesn't exist because A is not in the domain of f. So for this type of asymptotic discontinuity, it's actually breaking both 1 and 2. But these are the types of discontinuities that we'll see. We'll explore a little bit further. In a minute, I'll give a definition of continuous. We say a function is continuous. Maybe we'll jump to it. A function is continuous if it's continuous at each point in its domain. So every point. And the idea, roughly speaking, is if a function is continuous, you can draw it without taking your pencil off the paper. So here, we have to take our pencil off the paper to get this up here. In the jump, we have to take our pencil off the paper to jump. And here, we have to take the pencil off the paper to get to the other side of the asymptote. Okay, let's look at some examples. So a classic example, and this is one we've looked at a little bit already, the function sine of x over x. And if you graph this, the graph looks like this. But you can't divide by 0, so there's a hole here. And if you remember, when we started limits, we had a theorem that the limit as x goes to 0 of sine of x over x equals 1. And this value here is, in fact, 1. So in this case, f of 0 is undefined. And remember, the first condition for continuity, if we go back to our definition, we need the limit to exist, and we need the limit, that limit, to equal the function's value at a. So the limit, in our case, we're looking at 0. So we need the limit as x goes to 0 of f of x to be equal to f of 0. And so notice here, the limit as x goes to 0, so as we come in from the left or the right, the limit is 1, but the function has a hole. So we would need the function value, f of 0, to be equal to 1 for this to be continuous at 0. So this has a discontinuity. At x equals 0. Now that being said, we give a special name to this kind of discontinuity, specifically to the hole type discontinuity. And that's because if you look at this picture, you might think, we can fix that pretty easily. Just fill in the dot. If you go back to these other two cases, you can't fix this jump without dramatically changing the function. You can't fix this asymptote without dramatically changing the function. When you have a hole, all you got to do is just move, in this case, move this dot down to where this hole is. In this example we just did, just fill in that hole. And we give that a special name. We call that a removable discontinuity. So the formal definition of removable discontinuity is f has a removable discontinuity at a if you can find a function capital of f of x that fixes it. So everywhere besides x equals a, the two functions match, but capital F is repaired. It's a repaired version of little f, in that it is continuous at a. So this previous example, remember, we'll just draw it again. Sine of x over x looks like this. But it had that hole at 1. And intuitively, what we said before was just fill in the hole. And that's exactly what we do. We define the new function, capital F of x, to be the previous one if x differs from 0, and fill in the hole if x equals 0. So this new function, just by definition, is equal to the old function everywhere except when x is 0, and then we fix it when x is 0. And so that's the definition of a removable discontinuity. If there exists a function, capital F, that repairs that discontinuity of the old one. And it's really just going to be the case of when your function has a hole. So when you see questions that ask you if a continuity is removable, and can you find the function that fixes it, this is the idea. You repair the function at the trouble spot. Okay, let's go through some more examples. F of x equals 1 over x, a classical example that has a discontinuity at 0. So we know that the graph of 1 over x looks like this. And we see that it has an asymptotic discontinuity at x equals 0. And going back to the definition of continuity, the limit, in this case, as x goes to 0 of 1 over x, does not exist. The limit coming from the left is going to be, also doesn't exist. It will be positive infinity. The limit coming from the right will be positive infinity. The limit coming from the left is negative infinity. Those two don't match. So this thing does not have a limit. And that's the first part of the definition of continuity. You need the limit to exist, to be continuous at a point. This, again, is what we often will call an infinite discontinuity. Another classic example, 1 over x squared. We know this function looks similar to 1 over x in the first quadrant, but then it's brought up from the third to the second quadrant. So this is similar. This also has a discontinuity at x equals 0. And again, it's because the limit does not exist. The limit as x goes to 0 of 1 over x squared, that's an infinite limit. And remember, when we say a limit is infinite, that is a characterization of a type of limit that doesn't exist. We often write it this way. But what we really mean when we write this is that this limit doesn't exist, but it has this unbounded infinite behavior, this asymptotic behavior near 0. So because of this, the function has a discontinuity at x equals 0. And again, this would be another example of what we had just called an infinite discontinuity. We mentioned this, jumping ahead a little bit, a few minutes ago, but we say the function f is continuous as a function if it's continuous at every point in its domain. And again, roughly speaking, you can think of that as to draw the graph of the function. You put your pencil on the paper once, you draw it, and then you're done. You don't have to draw take your pencil off the paper, put it back on, and draw more. Okay. As a corollary, we have rules for function continuity. So if you have continuous functions f and g, and c is a constant, then you can multiply the function by a constant, you can add them, you can subtract them, or you can multiply them. And the result will still be a continuous function. So a classical example here, we can say f of x equals x is continuous. So that's just the 45-degree line, y equals x. But you can then take something like a polynomial and think of it as x times x times x plus 2x times x minus 1. And everything here, every operation, is coming from addition, subtraction, multiplication, or scalar multiplication of a function x that is continuous. So that means this is continuous. using this theorem. So a generalization of this idea, that this specific polynomial is continuous, is that every polynomial function is continuous. So what's written here, this p of x, is just a general way of writing a polynomial. So these bn's, bn minus 1, down to b2, b1, b0, those are just coefficients. N is the highest power of x in the polynomial, and then we work our way down. So if you had a fifth degree polynomial, x to the fifth, this n would be 5. And the bn would be the coefficient of that x to the fifth term. And it is true that every polynomial function is continuous as a function for every x. The next step from there is to take ratios of polynomials, and we call those rational functions. So any rational function, again, defined as the ratio of two polynomials, so p and q, the numerator and denominator, are polynomial functions. Any such rational function is continuous everywhere except where you have a division by 0. If you have a division by 0, there are two possibilities. So think of it a point x equals a, where you have a division by 0 here. One case is that you have an infinite discontinuity at a, as long as the numerator is non-zero. If the numerator is also 0, you have what's called an indeterminate form. But that's one possibility. If the numerator is something non-zero and you have a zero value, a value that makes q 0, then you have an infinite discontinuity. You may have an infinite discontinuity. The other possibility is you have a removable discontinuity, or a hole. So you'll have one of two types of discontinuities: infinite discontinuity or a hole if this denominator is 0. You won't have a jump. So let's see how this works with an example. So here we have a rational function, and we'll want to draw this. But rational functions like this are often much easier to handle if you look at factoring where you can. And we see the denominator factors to x plus 1 times x minus 2. Now, written the way the function is, we're not going to cancel these. And you note that if you plug in x equals minus 1 or x equals 2, you have a 0 in the denominator. And let's take a look at the function. If you did cross these x plus 1s, you would just have the function 1 over x minus 2, which is actually the function 1 over x shifted over 2 units. However, we have to note that because of this division by 0, if we plug in x equals minus 1, we have a hole here at minus 1, at x equals minus 1. So this function has an infinite discontinuity at x equals 2. But remember, these holes, we talked about calling them removable discontinuities because we can fix this. So we can come up with a repaired version. And if we note that let's call it, say, well, capital F of x equals, and just define it as the function as if we cancel the x plus 1 terms, 1 over x minus 2. This is the function that repairs the hole in f of x at x equals minus 1. If you graph this function, this function looks just like the one we just drew, just like the graph of little f, except there's no hole. And so this is how we can formally conclude that this was a removable discontinuity, because this is the function here that repairs it. This function matches, this capital F of x matches little f of x at every x, and it also, every x except the trouble spot, but it fixes things at the trouble spot. So because of that, we conclude that this original f, this original little f, has a removable discontinuity at x equals minus 1. The existence of this function that repaired this spot is what gives us that conclusion. Okay, let's take a look at trigonometric functions. Sine of x and cosine of x, both continuous functions on their whole domain. And intuitively, this makes sense if you think about drawing the graph of, say, sine of x. You can draw the graph without taking the pencil off the paper. There are no holes, there are no vertical asymptotes, there are no jumps. Also true for cosine of x. To show this for sine of x, we want to show that for any a, the limit as h goes to 0 of sine of the quantity a plus h equals sine of a. If we can show that, that will suffice to show that sine of x is continuous at a, but then because a was arbitrary, a could have been anything, so it's continuous at every value a. And what this is doing is saying, on the right-hand side here, this is the function evaluated at a. And then this, by letting h go to 0, we're actually getting, you could write here the limit as x goes to a of sine of a. This is an equivalent way of expressing that limit. So if we can show this, we can show that the function is continuous at a, and therefore anywhere, because again, a was arbitrary. So let's start out with that. Limit as h goes to 0 of sine of a plus h. And we're going to use a trig identity So the trig identity is sine of a plus h will be sine of a cosine of h plus cosine of a times sine of h. So this is a trig identity you would have learned in pre-calculus. And now we start to use our limit laws. So the limit of this sum will be the sum of the limits. Again, because those limits themselves will exist. So this is the limit as h goes to 0 of sine of a times cosine of h. Then we have plus the limit as h goes to 0 of cosine of a times sine of h. We can then notice that these terms involving a, there is no h involved there. So as far as the limit goes, these terms containing a but not h are constant, and so they can be factored out of the limit. So this becomes the limit as h goes to 0 of cosine of h, all of that times what we factored out, sine of a, plus the limit as h goes to 0 of sine of h, and in this case we factored out the cosine of a. And remember, we know that as h goes to 0, cosine of h has a limit of 1. As h goes to 0, sine of h has a limit of 0. So this is sine of a, which is what we wanted to show. So this is showing that the function value, so the function sine of x, evaluated at a, sine of a, is equal to the limit as we hone in on a of sine of a plus h. So this gives us that sine is a continuous function. And again, cosine has a very similar proof to show that it is a continuous function. Things are not as nice for the other four trig functions. And the reason why is you're dividing. So for instance, tangent of x, which we know is sine of x over cosine of x, you have a 0 in the denominator every time cosine of x is 0. And cosine of x is 0 quite a few times. So remember, cosine will look like this. And let's remember where the zeros of cosine are. The first 0 is here at pi over 2. The second 0 is at 3 pi over 2. Here we have 5 pi over 2. Over here, we have minus pi over 2, minus 3 pi over 2. So at each one of these points, these x values, cosine has a root. Specifically, any odd multiple of pi over 2, 1 times pi over 2, 3 times pi over 2, 5 times pi over 2, minus 1 times pi over 2, minus 3 times pi over 2. Well, how do you get an odd number? You take an even number. So take any integer n and double it, and then add or subtract 1 to shift it over. So any odd multiple. So for any n in z, some notation, when we write bold, math bold z like this is the symbol for the integers. And when we write an epsilon like this, we read this as is an element of. So if you take any n that is an element of the integers and plug it in here, this results in an x value at which cosine has a root. So these are the values of x where cosine of x equals 0. So because of that, the tangent function has a discontinuity for every value of x where its denominator, cosine of x, is 0. And you've seen this in your trig class, but if we line this up with the graph above it, So again, pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, minus 3 pi over 2. These are all the points at which cosine of x is 0. These values will be vertical asymptotes for the tangent function. And we'll choose a different color. The tangent function will look like this. So again, because of these roots of cosine of x happening at these odd multiples of pi over 2, we get asymptotic or vertical discontinuities, infinite discontinuities for tangent of x at those same values. So tangent of x has infinite, I should be a little bit more careful, we'll say has an infinite discontinuity for every x equals 2 times n plus 1, that quantity times pi over 2 for n in the integers. In other words, at every odd integer multiple of pi over 2. So again, you learned this in your pre-calculus, in your trig course, but we're now officially calling these vertical asymptotes discontinuities, or in this case, infinite discontinuities for the function tangent of x. And this will be echoed through cotangent and also secant and cosecant. Because each one of these 4 trig functions is dividing by a sine or a cosine, you get this set of infinite discontinuities for these. The last result we'll look at deals with composition. And it's a fairly simple idea. If you have 2 continuous functions and you compose them, the result is continuous. So g of x and f of x continuous. It's easiest enough to think of this. So for all x, then we'll say all x in the reals, the kind of nice case. Then f of g of x and g of f of x are also continuous. That's the easiest way to think of it. Here, this is a little bit more particular of a definition because we're talking about at a, so at a point x equals a. And we're saying, notice we're saying here that g is continuous at a, so that gives you g of a. But then f is continuous at g of a, which means you can feed this g of a to f. So we can use the fact that f is continuous at g of a. And then this is the idea, this composition. This is another way of writing this f composed with g at a. So g of a is continuous, so there's no trouble here. And then you feed that to f, which is continuous at g of a, so this composition is fine. This composition is continuous. Basically, the idea is when you have two continuous functions where everything is hunky-dory at a point, there's no jump, there's no vertical asymptote, there's no infinite discontinuity, composing continuous functions with one another does not, out of the blue, produce any of these types of discontinuities. They don't just define these discontinuities. You have to have a discontinuity introduced by one of these functions. The composition of the two will not cause it. Again, as long as both are continuous. Oftentimes we'll see examples like this. Find the set on which this function here is continuous, and this function is the composition. You could call this inner function, maybe we'll call this our h of x. And then f of x, the outer function, would be x to the 4/3. So this g of x is equal to f of h of x. Now the outer function, this is continuous for all x. This is some more notation. Upside down capital A means for all. So this is continuous for all x in the reals. In particular, x to the 4th, you can always raise something to the 4th power, but then the cube root, right? We can think of this x to the 4/3 as x to the 1/3 to the 4th. And when you're taking a cube root, there's no restriction on an x being non-negative. So this works for any x. And then you can always raise that to the 4th power. So this is continuous for all x. So for this overall function, g, this composition of the two, to be discontinuous, the problem would have to come from what's inside. And when we look inside, two natural things to think of is square roots of negative numbers that we have to avoid, or division by 0. But note that the denominator, note the terms, x to the 4th, that's always greater than or equal to 0. Second term, x squared, always greater than or equal to 0. Well, 1 is strictly greater than 0. If you add these three up, x to the 4th plus x squared plus 1, well, that's got to be strictly bigger than 0. Which means here we can have no division by 0. So this function, the outer, again, this function is this composition. The outer function, x to the 4/3, is fine. There's no issue there. There's no type of discontinuity with that function. And for the inner function, the only type of problem we can have for a rational function is if the denominator is 0. And there's no x for which that can happen because of what we just saw here. So that means that this function, well, maybe we should say here, this means this inner function, this h of x, is x over x to the 4th plus x squared plus 1, is also continuous for all x in the real numbers. And by our previous theorem, the composition of the two, this given g of x, is also continuous for any real x by our previous theorem. So a lesson to take from this was a specific example, but when you're asked to find the points of discontinuity of a function, you generally want to look at the function and think, how does that break? Where can there be trouble spots? Where am I up against the edge of the domain Where would you cross into the taking a square root of a negative number, or dividing by 0 is another typical issue. Anything that causes the function problems will generally lead to some type of discontinuity. Now, this idea of discontinuity, or rather of continuity, is the first step. Well, I should say the step just before getting into the main topic of this course, which is the idea of derivative. So continuity, remember, a function is continuous if we can draw it without taking the pencil off the paper. And what we're going to get into now, or next, is pick a point and draw the tangent line at that point, if it exists. And the question is then, what's the slope of that tangent line? And remember, that's the driving question for this course. We talked about it early on. The driving question in this differential calculus course is the idea of the slope of a line that's tangent to a graph. And so we'll be getting into that soon.